Analyzing a building with 2 occupancies applying for electrical service from a utility company. The service equipment is located in one location, and there's a proposal for individual service drops from a 230 volts 3-phase transformer bank. The voltage, frequency, and phase characteristics are the same for both occupancies, and the capacity requirement for each doesn't exceed 500 amps. The service equipment installations are accessible to both occupants. The initial analysis suggests that this proposal could result in a double service drop, potentially violating National Electrical Code, or NEC, Article 230.2 number of services. NEC Article 230.2 generally prohibits more than one service to a building or structure. However, there are exceptions. One exception applies when the service is supplied by underground sets of conductors, size 50 mm and larger. These conductors, even if not connected together at their load end and thus not considered parallel conductors, are considered to be supplying one service. This exception allows for multiple service disconnects fed from a single service lateral in certain circumstances. The question is whether the initial analysis is correct that the proposal will result in a double drop, and what the rationale is for allowing individual service laterals for each service disconnect, not more than 6, grouped in one location. Firstly, let's address the double drop scenario. If each occupancy has its own distinct service drop directly from the utility transformer bank, it generally constitutes multiple services. This is because each drop represents a separate connection to the utility's distribution system. Unless an exception applies, this configuration would violate NEC 230.2. Secondly, the NEC allows for exceptions to the single service rule. The underground conductor exception, using 50 mm or larger conductors, is one such case. The rationale behind allowing individual service laterals for each service disconnect, up to a maximum of 6, grouped in one location, is multifaceted. One potential reason is to provide flexibility in system design and maintenance. With multiple disconnects, individual circuits or portions of the building's electrical system can be isolated for maintenance or repairs without disrupting the entire building's power supply. This enhances reliability and reduces downtime. Another reason relates to overcurrent protection and system coordination. By having multiple service disconnects, the available fault current at each disconnect can be managed more effectively. This allows for the selection of overcurrent protective devices with appropriate interrupting ratings, ensuring that they can safely clear any potential fault current. Each service disconnect can be sized and rated according to the specific load it serves, optimizing the protection and performance of the electrical system. The question also raises the point of whether the exception for underground service laterals is based on the absence of service entrance conductors or to limit short-circuit current. Regarding the absence of service entrance conductors, it is important to clarify the terminology. Service entrance conductors are the conductors between the service point and the service disconnecting means. In the case of underground service laterals, the conductors from the utility's connection point to the service disconnect are indeed considered service lateral conductors, not service entrance conductors. This distinction is significant because the NEC treats service laterals and service entrance conductors differently in some aspects. The exception allowing multiple service disconnects from a single service lateral is partly based on the understanding that the service lateral provides a common point of supply. The multiple disconnects then provide the means to distribute the power to different loads within the building. As for limiting short-circuit current, this is a valid consideration. The use of multiple service disconnects can help to limit the available fault current at each disconnect, which can simplify the selection of overcurrent protective devices. However, it is not the sole reason for allowing multiple service disconnects. The overall design and coordination of the electrical system must consider the available fault current, the interrupting ratings of the protective devices, and the need for selective coordination to ensure that only the faulted portion of the system is isolated during an overcurrent event. The NEC provides guidance on how to perform fault current calculations and select appropriate overcurrent protective devices. In summary, the initial analysis is likely correct that the proposal for individual service drops for each occupancy could violate NEC 230.2. However, the exception for underground service laterals using 50 mm2 or larger conductors could potentially be applicable if the installation meets the specific requirements of the code. The rationale for allowing multiple service disconnects from a single service lateral is based on factors such as system reliability, flexibility, overcurrent protection, and the management of fault current. The design of the electrical system must comply with all applicable requirements of the NEC and other relevant standards to ensure safety and performance. The service point is defined as the point of connection between the serving utility and the premises wiring. The service conductors are the conductors from the service point to the service disconnecting mean. These conductors can be either service drop conductors, which are overhead conductors, or service lateral conductors, which are underground conductors. The service disconnecting means is the device or devices used to disconnect all ungrounded conductors of a service from the premises wiring. It is typically a circuit breaker or a fuse switch. The number of service disconnecting means is limited to 6 per service, as specified in NEC 230.2. This requirement is intended to simplify the process of disconnecting the entire service in an emergency or for maintenance purposes. The service equipment includes the service disconnecting means, overcurrent protective devices, and other equipment intended to protect the service. The service equipment must be suitable for the available fault current at the service point. The available fault current is the maximum current that could flow in a short circuit condition. It is determined by the utility company and must be considered when selecting overcurrent protective devices. Overcurrent protective devices are devices that are designed to interrupt the flow of current in an overcurrent condition such as a short circuit or an overload. These devices can be either fuses or circuit breakers. Fuses are one-time devices that melt and interrupt the current flow when an overcurrent occurs. Circuit breakers are reusable devices that trip and interrupt the current flow when an overcurrent occurs. The interrupting rating of an overcurrent protective device is the maximum fault current that the device can safely interrupt. The interrupting rating must be greater than or equal to the available fault current at the point of installation. Selective coordination is the process of designing an electrical system so that only the overcurrent protective device closest to the fault will trip, leaving the rest of the system operational. Selective coordination is important for ensuring that critical loads are not unnecessarily interrupted during an overcurrent event. The National Electrical Code, or NEC, is a set of standards for the safe installation of electrical wiring and equipment in the United States. The NEC is updated every 3 years and is adopted by many states and local jurisdictions. It is essential for electrical engineers and contractors to be familiar with the NEC to ensure that their installations comply with the code and are safe. Article 230 of the NEC covers service entrances. This article provides requirements for the size and type of service conductors, the location of the service disconnecting means, and the grounding of the service. It also covers the number of services allowed per building or structure. When dealing with multiple occupancies in a single building, the NEC provides specific guidelines regarding service requirements. Each occupancy is generally permitted to have its own service provided that certain conditions are met. These conditions typically involve the separation of occupancies by fire-rated walls or other approved means. If the occupancies are not separated, then the building is typically considered to be a single occupancy and only one service is permitted. However, there are exceptions to this rule, such as the exception for underground service laterals. The NEC also addresses the issue of parallel conductors. Parallel conductors are two or more conductors that are connected together at both ends to form a single conductor. Parallel conductors are permitted under certain conditions, such as when the conductors are size 1/0 American wire gauge, or oak, or larger and are installed in the same raceway or cable. When parallel conductors are used, they must be sized and installed in accordance with the NEC requirements. The goal of these requirements is to ensure that the parallel conductors share the current equally and do not overheat. In the scenario presented, The proposal for individual service drops for each occupancy could be problematic unless the underground service lateral exception applies. The electrical system designer must carefully consider the NEC requirements and ensure that the installation complies with the code. The designer must also consider the available fault current, the interrupting ratings of the overcurrent protective devices, and the need for selective coordination. The designer should consult with the utility company to obtain information about the available fault current at the service point. The designer should also perform fault current calculations to determine the required interrupting ratings of the overcurrent protective devices. Finally, the designer should ensure that the electrical system is properly grounded in accordance with the NEC requirements. Grounding is essential for providing a path for fault current to flow back to the source, which helps to trip the overcurrent protective devices and prevent electrical shock hazards. The grounding system must be properly sized and installed to ensure that it can effectively carry fault current. In addition to the NEC, there may be other applicable codes and standards that must be considered. These codes and standards may vary depending on the location of the building and the type of occupancy. It is important to consult with the local authorities to determine which codes and standards apply. The electrical system designer should also be familiar with the utility company's requirements for service connections. The utility company may have specific requirements for the location of the service equipment, the type of service conductors, and the grounding of the service. The designer should work closely with the utility company to ensure that the service connection meets their requirements. The design of an electrical system for a building with multiple occupancies can be complex and challenging. It is important to consult with qualified electrical engineers and contractors to ensure that the system is designed and installed safely and in accordance with all applicable codes and standards. The selection of service equipment depends on several factors, including the size of the load, the available fault current, and the desired level of reliability. The service equipment must be properly sized to handle the expected load and must be protected against overcurrents. The service equipment must also be suitable for the environment in which it is installed. For example, service equipment installed in a wet location must be suitable for wet locations. The installation of service equipment must be performed by qualified electricians in accordance with the NEC and other applicable codes and standards. The electricians must be properly trained and experienced in the installation of service equipment. The installation must be inspected by a qualified electrical inspector to ensure that it complies with the code. Regular maintenance of service equipment is essential for ensuring its continued safe and reliable operation. The maintenance should include periodic inspections, testing, and cleaning. Any damaged or worn components should be replaced promptly. The maintenance should be performed by qualified electricians in accordance with the manufacturer's recommendations. When troubleshooting electrical problems, it is important to follow safe work practices. Always disconnect the power before working on electrical equipment. Use properly insulated tools and equipment. Wear appropriate personal protective equipment, such as safety glasses and gloves. If you are not qualified to troubleshoot electrical problems, contact a qualified electrician. Electrical safety is paramount. Always follow safe work practices and consult with qualified professionals when working with electricity. Improperly installed or maintained electrical systems can pose serious safety hazards. The information provided here is for general guidance only and should not be considered a substitute for professional advice. Always consult with qualified electrical engineers and contractors for specific advice regarding your electrical system. Remember, electricity is a powerful force that must be treated with respect. By following safe work practices and complying with all applicable codes and standards, you can help to ensure the safety of yourself and others. The NEC is a living document that is constantly evolving to reflect new technologies and safety concerns. It is important to stay up to date on the latest changes to the NEC to ensure that your electrical installations comply with the code. There are many resources available to help you stay informed about the NEC, including the National Fire Protection Association, or NFPA, the International Association of Electrical Inspectors, or IAE, and various online forums and publications. By taking the time to educate yourself about the NEC, you can help to improve the safety and reliability of electrical systems. Consider the specific application and the potential hazards involved when designing and installing electrical systems. There is no one-size-fits-all solution, and it is important to tailor the design to the specific needs of the situation. Always prioritize safety and ensure that all work is performed by qualified professionals. By following these guidelines, you can help to create safe and reliable electrical systems that will serve their intended purpose for many years to come.